Welcome students. Today we shall discuss about the modes of a rectangular cavity resonator. During the last lectures we studied about the modes, uh, what is a cavity resonator, what is a physically what is a cavity resonator, and we solved its its uh, dimensions and a bit of mathematics. Today we shall focus more on how uh, frequencies and modes are generated in a rectangular cavity. Here we see a rectangular cavity with dimensions x, y, z, and x dimension is here of the length 2a, it is of 2b, and the z direction is b. It is made of a conducting material, metallic, and here you know that in electromagnetic wave the electric field lands normally on the surface, so the tangential component will be 0 on of the uh, each of the side walls here. And there are two types of cavity: closed and open cavity. In open, what happens? It can go here, the electromagnetic wave can propagate this way, but in closed cavity we have these walls also closed. Let us see here how during the last lecture we noted the formation of standing waves. Here we will focus more on how the frequencies are generated. So here the oscillation frequencies of various modes of the closed rectangular cavity we can easily find the frequency by using the propagation constant. Here V is equals to C by the refractive index, velocity of light divided by the refractive index of the active medium present in this. So we can realize it: kx square plus ky square plus kz square, the propagation constant along the three dimensions. It can be easily solved. Here kx is m pi by 2a, it is n pi by 2b, and it is q by d. This we have already seen. So omega square is equals to c by n naught squared pi square, and rest all this within the bracket. Further we solve omega is equals to c pi by n naught, and under root of m square by 4a square n square by 4b square plus q square by d square. So Further, see the allowed frequencies of oscillation of the field in the cavity. These are the allowed frequencies. You see, it depends on the index of refraction of the active material and the dimensions of the cavity. A, B, and D means all the three dimensions. So the field configurations represent standing wave pattern in the cavity, and these are called the modes of oscillation of the there is an electromagnetic wave, that light, it is actually an electromagnetic wave, a part of the wide and vast electromagnetic spectrum. So here they represent only the possible frequencies that can exist within the cavity. For example, we have seen the black body radiation spectrum, and due to Planck, and you recall that u nu du nu, that means the energy within the energy density within a frequency range d nu, it must be 8 pi n naught by c, that means 1 by v velocity cube nu square d nu. So we have, if we put the velocity of light here in place of c, n naught we assume 1, and nu is equals to 3 into 10 to the power 14 hertz in the visible range, then d nu must be 3 into 10 to the power 9 hertz. Substituting all this, we obtain the energy density within the given frequency range, 2 into 10 to the power 8 per centimeter. It is a vast, it is very big quantity, and for a 10 centimeter cube cavity, we see how many modes can be set up. 2 into 10 to the power 9, it is a quite large number. So typical dimensions of a cavity, we have assumed this, and to achieve a very small number of possible oscillating modes within the line width of the atomic transition, the volume of the cavity has to be made very small. We shall shortly see this also. For a single mode of oscillation within the line width, what must be the volume? The volume must be of the order of micrometer. If we take the volume as 5 into 10 to the power minus 9 centimeter cube, then then uh, for if we have the dimensions 17 micrometer, then the volume comes out to be 17 cube, and approximately we have the volume this. So optical microcavities with micrometer small dimensions can be fabricated. This falls in the field of cavity quantum electrodynamics. This prevents the spontaneous emission. In conventional lasers, volume of cavity is quite large. Number of oscillating modes within the line width of the atomic transition is very large. It is quite large. Oscillating modes can draw energy from the atomic system. Emission, therefore, the emission cannot be monochromatic. So we see in the conventional lasers because volume is quite large, so monochromaticity cannot be maintained. For a very few oscillating modes, the dimension of the cavity chosen are of the order of lambda, the wavelength of the radiation. So, volume of atomic system for lasing becomes quite small. So, the required power is also very. What about the open cavities? Using these, the extremely large number of oscillating modes can be overcome. This consists of a pair of plane curved mirrors facing each other like this. This is the active material and these are the mirrors. One mirror is, it is 100% reflecting, and this is 90 or more than 90% reflecting. So the output we may get from here. Now, using these, the extremely large number of oscillating modes can be overcome, and we can limit it to very few modes. It consists of a pair of plane or curved mirrors facing each other. Angles made by the component plane waves within the x, y, and z x, y directions. So the it must not be very large. It is like this. So it is mostly confined to the axis of the resonator. In open resonators, wave propagates only along z direction because Q is large. We have the integers m and n small, and to avoid the losses in the cavity, to prevent the losses, the modes are limited so that they make very small angle in the axis of propagation, so that the energy is confined to the axis and the loss is kept very small. We see here only the paraxial rays. Paraxial rays are there and small values of m and n, which implies small loss. only these modes will be able to oscillate within the cavity. Modes M and N, when they are large, they will have large loss and uh, unable to oscillate. In rectangular cavity, if rectangular cavity is open, all modes will be lossy. If it is in open cavity, all modes will be lossy. Here we assume that our cavity supports only the mostly the longitudinal modes, and the transverse modes are very limited. So M and N are the integers corresponding to the transverse modes, and therefore M and N is very smaller than Q, the longitudinal direction. So we are considering an open resonator cavity in which we have the resonator closed only from the side wall, and it can go, the beam can go along the z axis. So there is an approximation. Of course, by simple mathematics, we see omega is equals to c pi by n naught. Q by d we have dragged out of the bracket, and what remains inside 1 plus m by 2a squared plus n by 2b squared divided by q by d squared and whole under root. Simplifying it, because omega is equals to 2 pi nu, because all the three integers are involved here. We have, and applying the Taylor approximation of the series, we see, because here q is quite large, c pi by n naught q by d 1 plus half d by q squared 1 by 4, and here 1 by 2 1 by 2 squared. So here we get 1 by 4, and the rest is within the bracket. Simplifying it, we see c by 2 n naught q by d and 1 plus half d by q square bracket m square by a square plus n square by b square, and finally we get c by n 2 n naught q by d bracket m square by a square plus n square by b square into d by 8q by multiplying it within. Here k is equals to this thing we already seen. Omega is 2 pi nu, 2 pi n naught by lambda, because c by nu is equals to. As far as spherical mirror resonators are concerned, in our earlier lecture, one of the earlier lectures, we studied about the spherical closed curved resonators, and we obtained the stability condition therein. So, in symmetrical confocal, we have a pair of identical concave mirrors, each having a radius of curvature capital R, and the separation between the curved mirrors is also R. Therefore, the foci are centered at the center of curvature. These are the these are called the symmetrical confocal. In symmetric concentric, what happens? Identical concave mirrors of radii of curvature R, but the distance between them is 2R. Here it was R. So it was symmetrical confocal. That means the focus is coinciding. Here in this concentric, the centers coincide. What is a stable resonator? We have already done an analysis for this. A family of light rays may keep bouncing back and forth between the mirrors of the cavity indefinitely without ever escaping from the cavity. We obtained the stability condition. And what is an unstable resonator? The ray diverges away from the axis after every pass. Thus, it finally escapes from the resonator after a few traversals. And if it cannot escape, it goes to the lossy mode. Modes of a stable resonator are given by the Hermite-Gauss equation. EMN is equal to E naught H Hermite polynomial HM HN is a function of capital X, of capital Y, and you see here it is the Gaussian function. EMN is equal to E naught HM HN e raised to minus R square by omega naught square. Here capital X is equal to under root of 2 x by omega naught, and capital Y under root x small y by omega naught. M and N are the transverse mode numbers. Omega naught is the characteristic mode width, and it depends on the wavelength of the monochromatic radiation. Radii of mirrors depends on lambda, and radii of mirrors between the and the distance between the mirrors. Omega naught characteristic mode width. Gaussian lowest order mode is E naught because HM and HN they become 1. E naught exponential minus R square by omega naught square. So this is the lowest order mode, and which is the most prominent mode for a rectangular closed cavity, and even for a stable resonator curved mirror. So we have the lowest order. Now further we see the difference in frequency. If m and n are same and q values differ by 1, we see the frequency for that particular mode number. For example, you see here nu mn q plus 1, it is just by substituting it in the earlier equation we obtain this equation. Then for nu m and q we obtain just substituting and subtract it, we obtain c by 2 n naught. This we have neglected. 1 by d, that means delta q naught, delta nu q is nearly equal to c by 2 n naught d. It is the longitudinal mode spacing in rectangular cavity. Longitudinal means here along the z direction. So we see it depends on the on the on the longitudinal direct dimension. You see here d. So it is delta nu q is equals to c by 2 n naught d. It is the longitudinal mode spacing, and neglecting mn, in general we can write q by c 2 n naught d, because now it depends on q. Here if we neglect this, and it is mostly confined to the axis we call the paraxial rays. For example, to compare it with the with the modes of a mechanical system, we see that frequency of oscillation of a stretched string of length d, there will be as many half wavelength vibrations modes as mathematically we see that q half wavelength q lambda by 2 must be equal to the dimension of the cavity, and q by 2 c by nu it must be d, and nu is equals to q c by 2d. This we have seen in our elementary physics, and this equation goes hand in hand with that concept. Just we have here it is the velocity of light, here it may be velocity of sound, here it is n naught. So c by n naught is actually c by n naught is actually v. So it is not much different from this for sound wave or acoustics. Now the question is there, how modes are selected? Conventional resonators have dimensions large compared to the optical wavelength. A large number of modes which fall within the gain bandwidth of the active medium and which can oscillate in the laser can be set up, therefore, because the cavity dimensions are large. The output may consist of various transfers in longitudinal modes, longitudinal this direction and transfers this direction. Greater divergence of the output beam takes place that consists of a number of oscillating frequencies. The output power is maximum when laser oscillates in a single mode, which is the fundamental, and that is usually Gaussian mathematics. So for now, it is this much. You see it from any book, and you may refer Tyagarajan and Ghatak also, Swalto, Yeri, Demtroder, and we shall meet during the next lecture. Thank you very much. Thank you.